Imagine if tomorrow it started raining and didn't stop for 2 million years. Not just a drizzle, not just a storm, but a relentless deluge that transformed every continent, every ecosystem, every living thing on our planet. This isn't science fiction. This actually happened, and it changed the course of life on Earth forever. Tonight, we journey back to one of the most extraordinary chapters in our planet's history. A chapter that was hidden in stone for millions of years until geologists stumbled upon evidence so shocking, so impossible, that it rewrote everything we thought we knew about ancient Earth. This is the story of the Carnian pluvial episode, the 2 million-year rain that turned a barren desert world into a thriving paradise and gave birth to the age of dinosaurs. What you're about to discover will challenge everything you've been taught about how life evolves, how ecosystems transform, and how quickly our planet can change. We'll explore how massive volcanic eruptions triggered a climate catastrophe that somehow became Earth's greatest blessing. We'll witness the rise and fall of entire species, the birth of modern coral reefs, and the moment when dinosaurs went from insignificant creatures hiding in the shadows to the rulers of the world. But this story begins in a place you wouldn't expect. Not in some exotic location, but in the Austrian Alps, where two geologists made a discovery that would shatter our understanding of ancient history. Their find was so puzzling, so out of place, that it took decades for science to accept what the rocks were trying to tell us. And what they revealed was a world more alien and more dramatic than anything we could have imagined. The year was 1975, and geologists Wolfgang Schlager and Matthias Schöllenberger were conducting routine fieldwork in Austria's northern limestone Alps. They expected to find the usual carbonate rocks that had been forming in this region for millions of years. Instead, they discovered something that shouldn't exist. Embedded within the pristine white limestone was a layer of dark grey rock, completely different in composition and character from everything around it. This wasn't just unusual, it was impossible. The dark layer contained high levels of silica and clay minerals, the kind of deposits you only find in areas with intense rainfall and massive erosion. But according to everything scientists knew about this period in Earth's history, 234 million years ago, this region should have been bone dry. The entire planet was locked in one of the most severe droughts in geological history. The two Austrian scientists had stumbled upon evidence of the impossible. They'd found proof of rain in a world that wasn't supposed to have any. But this was just the beginning. As word of their discovery spread through the geological community, similar findings began emerging from around the globe. The same mysterious dark layer was found in southwest England, embedded within red sandstone formations. It appeared in Israel, in Italy, and thousands of miles away in Utah. Each discovery painted the same impossible picture. Everywhere geologists looked, they found evidence of massive rainfall during a time when Earth was supposed to be a global desert. The evidence wasn't subtle. These weren't traces of occasional showers. The rock record spoke of torrential, continuous precipitation that lasted for geological ages. To understand just how shocking this discovery was, you need to picture Earth as it existed 234 million years ago. Our planet looked nothing like the blue marble we know today. All the continents were fused together into a single supercontinent called Pangaea, stretching from pole to pole like a massive scar across the planet's surface. This wasn't the lush green world we inhabit. Pangaea was a hellscape of desert that made the Sahara look like a tropical paradise. The interior of this supercontinent was completely cut off from the ocean by towering mountain ranges that blocked moisture from penetrating inland. Only the coastal regions received any meaningful rainfall, Everything else was an endless expanse of red sand and barren rock, baked under a sun that shone in skies 10 degrees Celsius hotter than today. The oceans themselves were like vast cauldrons, with surface temperatures reaching 47 degrees Celsius. That's hotter than most hot tubs, too hot for most marine life as we know it. In this harsh world, life clung to existence in small pockets of habitability. The dominant plants were small, drought-resistant species that could survive months without water. Animals were mostly primitive reptiles, early mammals, and the very first dinosaurs. But these dinosaurs were nothing like the giants we imagine. They were small, rare creatures that lived in the shadows of more successful reptile groups. This was the world that the Austrian geologists thought they understood. A world locked in perpetual drought, where rain was a precious rarity and life was a constant struggle against dehydration. But the dark rock layer told a completely different story. It spoke of a world transformed by water, a world where rain fell so heavily and so continuously that it carved new river systems, created vast inland lakes, and turned the global desert into a waterlogged paradise. The evidence kept mounting. Geologists found fossilized river channels where no rivers should have existed. They discovered ancient lake beds in the heart of what should have been desert. Most remarkably, they found coal deposits, the compressed remains of vast swamp forests in regions that should have been too dry to support a single tree. But perhaps the most telling evidence came from a substance that most people have never heard of, but that tells one of the most important stories in Earth's history. Scattered throughout these mysterious rock layers, scientists found deposits of kaolinite, a white powdery clay that forms only under very specific conditions. Kaolinite requires intense chemical weathering, the kind that happens when hot, humid climates cause rocks to break down rapidly. Its presence in these ancient layers was like finding snow in the desert. It simply shouldn't be there. As the evidence accumulated, scientists began to realize they were looking at something unprecedented in Earth's history. This wasn't just a brief wet period or a regional weather anomaly. The rock record suggested a global climate transformation that lasted for over 1 million years. Floods alternated with periods of drought in cycles that repeated again and again, creating an era so severe and so transformative that it earned its own name in the geological timescale, the Carnian pluvial episode. The scale of this event was almost incomprehensible. For comparison, the last ice age, which dramatically reshaped continents and drove countless species to extinction, lasted about 100,000 years. The Carnian pluvial episode lasted 20 times longer. It was a climate catastrophe that made the ice ages look like brief hiccups in Earth's history. But what could possibly cause such a dramatic and long-lasting change in global climate? The answer lay not on the surface of the Earth, but deep beneath the ancient Pacific Ocean, in one of the most violent volcanic episodes our planet has ever witnessed. The culprit was something called the Rangelia Large Igneous Province, a volcanic system so massive that its eruptions could be seen from space if humans had been around to witness them. These weren't ordinary volcanic eruptions. The Rangelia system was pumping out over 1 million cubic kilometers of molten rock, enough to bury the entire continental United States under a layer of lava several feet thick. The eruptions were so powerful that they injected vast quantities of carbon dioxide and other greenhouse gases directly into the atmosphere, triggering a cascade of climate changes that would reshape the planet. The volcanic carbon dioxide acted like a blanket around the Earth, trapping heat and driving global temperatures even higher than they already were. But the real transformation came from what happened to the water cycle. As temperatures soared, evaporation from the oceans increased dramatically. The superheated atmosphere could hold vastly more moisture than before, setting the stage for precipitation on a scale never before seen in Earth's history. When those atmospheric rivers finally reached the land, they unleashed fury beyond imagination. The rains that began falling weren't gentle spring showers or seasonal monsoons. They were torrential downpours that turned the ancient world into a waterlogged nightmare. Day after day, month after month, year after year, the skies opened and refused to close. Picture standing in the middle of Pangaea during this time. The air would be thick and oppressive, saturated with moisture that made every breath feel like drowning. The heat was suffocating, but the humidity made it unbearable. And always, always, there was the sound of rain. Not the pleasant patter of drops on a roof, but the deafening roar of water falling from the sky in sheets so thick you couldn't see 10 feet in front of you. The transformation was immediate and catastrophic. Ancient riverbeds that had been dry for millions of years suddenly roared to life, carrying unprecedented volumes of water and sediment across the landscape. These weren't the meandering streams we know today. They were raging torrents that could carve new canyons in a matter of centuries, moving mountains grain by grain into vast inland seas. The deserts that had dominated Pangaea for eons began to disappear under rising water tables. What had been endless expanses of red sand became muddy marshlands, then shallow lakes, then deep inland seas that stretched beyond the horizon. The geography of the planet was being rewritten in real time, and life had to adapt or perish. But here's where the story takes an unexpected turn. This wasn't just a catastrophe. It was also an opportunity on a scale that life had never encountered before. For millions of years, most of Earth's surface had been locked away from living things, too dry and hostile to support anything but the hardiest desert specialists. Now, suddenly, vast new territories were opening up. Fresh water was everywhere. Nutrients that had been locked in rock for eons were being washed into new environments, creating a biological gold rush. The first beneficiaries were the plants, species that had been clinging to existence in tiny refuges near coastlines, suddenly found themselves with unlimited water and space to expand. Ferns exploded across the landscape, their spores carried by the constant winds and rain to colonize territories the size of modern continents. Conifers, those early evergreen trees, began their march toward global dominance, establishing the first real forests in millions of years. These weren't the towering redwoods or dense oak forests of today. These were alien landscapes of primitive plants, creating ecosystems that had never existed before. Vast swamplands stretched for thousands of miles, filled with tree ferns as tall as modern oaks and conifers that looked more like giant bottle brushes than anything we'd recognize today. The air itself was different, thick with the smell of decomposing vegetation and the constant mist of evaporation. As these new forests grew, they began to change the climate even further. Plants are nature's air conditioners, and suddenly Earth had millions of square miles of new vegetation transpiring water vapor into the atmosphere. The forests created their own weather systems, generating local rainstorms that fed back into the global cycle of precipitation. It was a runaway process that fed on itself, turning a desert planet into a greenhouse world. But the most dramatic changes were happening in the oceans. The massive influx of fresh water from the continents was carrying with it unprecedented amounts of nutrients, minerals, and organic matter. The seas, which had been relatively barren during the long drought, suddenly became supercharged with the building blocks of life. This was the moment when the modern ocean ecosystem began to take shape. For the first time in Earth's history, tiny organisms called coccolithophores began to flourish in vast numbers. These microscopic creatures might seem insignificant, but they were about to revolutionize the planet. Coccolithophores build intricate shells of calcium carbonate, and when they die, these shells sink to the ocean floor, forming the limestone that would become the foundation of countless future ecosystems. Even more revolutionary was the appearance of dinoflagellates, microscopic organisms that would change the face of marine life forever. These tiny creatures developed one of the most important partnerships in biological history, forming symbiotic relationships with early corals. This partnership allowed corals to build reefs for the first time, creating underwater cities that would become some of the most diverse ecosystems on the planet. The chemical composition of the oceans was changing too. The massive volcanic eruptions weren't just pumping greenhouse gases into the atmosphere, they were also releasing enormous quantities of sulfur compounds and other chemicals that made the seawater more acidic. This might sound destructive, but it actually triggered a biological revolution. The new chemistry favoured certain types of organisms while eliminating others, creating ecological niches that had never existed before. In the deeper parts of the oceans, conditions became truly extreme. The combination of increased temperatures, changing chemistry, and massive inputs of organic matter from the land created vast dead zones, where oxygen levels dropped to nearly zero. These weren't temporary events. They persisted for hundreds of thousands of years, fundamentally altering marine ecosystems across the globe. Yet even in these seemingly hostile conditions, life found a way. New types of bacteria evolved to thrive in the oxygen-poor water. Chemical processes that had been rare became common, creating new food webs based on sulfur and methane rather than photosynthesis. The oceans were becoming alien, but they were also becoming more complex and diverse than ever before. The cycles of flood and drought created a pattern that would persist for nearly 2 million years. Just when ecosystems began to adapt to the constant rain, the climate would shift and drought would return. But these weren't the same kind of droughts that had dominated Pangaea before. These were different, occurring in a world that now had vast networks of rivers, lakes, and groundwater. Even during the dry periods, water was available in ways it never had been before. This constant environmental pressure created what scientists call an evolutionary arms race. Species that could adapt quickly to changing conditions thrived. Those that couldn't disappeared. The result was an acceleration of evolution unlike anything Earth had seen since the explosion of complex life hundreds of millions of years earlier. The stage was being set for one of the most important transitions in the history of life on Earth. In the shadows of this transformed world, a group of small reptiles that had barely managed to survive the harsh conditions of desert Pangaea were about to seize their moment. The age of dinosaurs was about to begin, and it would start with footprints pressed into the mud of an ancient lakeshore, preserved for us to discover hundreds of millions of years later. In the Italian Dolomites, high in the Alps where ancient seas once lapped against tropical shores, paleontologists have uncovered one of the most remarkable crime scenes in natural history. Preserved in layers of rock that were once the muddy bottom of a shallow lagoon are footprints. Thousands upon thousands of footprints, pressed into sediment that hardened into stone over the course of millions of years. These aren't just any footprints. They're a record of revolution written in three-toed tracks and claw marks. Below a certain layer of reddish mudstone, the prints tell one story. Above it, they tell another entirely. It's as if someone drew a line through time itself, separating the world that was from the world that would be. Below the line, the tracks belong to archosaurs, early relatives of crocodiles, and various other reptiles that had dominated the harsh desert world of early Pangaea. Their prints are scattered, sparse, the footprints of survivors eking out existence in a hostile landscape. These creatures had ruled the world not through dominance, but through endurance, clinging to life in a planet that seemed determined to kill everything on it. Above the line, everything changes. The mudstone tells a different story entirely. Suddenly the rock is filled with new types of tracks. Three-toed prints appear in abundance, pressed deep into what was once soft, wet mud. These are the footprints of dinosaurs, but not the massive thunder lizards of popular imagination. These are the tracks of creatures no larger than modern dogs, but they're everywhere. The timing is perfect, almost too perfect to believe. These dinosaur tracks appear exactly at the moment when the Carnian pluvial episode was reaching its peak intensity. The correlation isn't coincidental, it's causational. The Great Rain had triggered the first major extinction event of the Triassic period, and in the chaos that followed, dinosaurs seized their opportunity. To understand how dramatic this transformation was, imagine walking through a modern ecosystem and suddenly finding that all the large mammals had vanished overnight, replaced by creatures that had previously lived only in the shadows. That's essentially what happened during the Carnian pluvial episode, except the process took hundreds of thousands of years instead of a single night. The extinction wasn't caused by the rain itself, but by the cascading effects of environmental change. Species that had adapted perfectly to the arid world of Pangaea suddenly found themselves in an environment they couldn't handle. The constant flooding disrupted food chains that had been stable for millions of years. Plants that had evolved to conserve every drop of water were suddenly drowning in swamplands. Animals that had developed efficient kidneys to retain moisture found themselves in a world where water was so abundant it became toxic. The statistics are staggering. Paleontologists estimate that up to 33% of all marine species vanished during the Carnian pluvial episode. On land, entire families of reptiles disappeared forever. Rhynchosaurs, bizarre beaked reptiles that had been among the most successful herbivores of the Middle Triassic, were reduced to just a few specialized lineages. Dicynodonts, mammal-like reptiles with tusks and beaks, saw their diversity collapse dramatically. But extinction is only half the story. The other half is opportunity, and no group seized that opportunity more dramatically than the dinosaurs. These creatures had evolved about 20 million years before the Carnian pluvial episode, but they had remained bit players in the drama of Triassic life. They were small, rare, and seemingly insignificant compared to the dominant archosaurs and other reptile groups. The rain changed everything. As traditional ecosystems collapsed, new ones emerged from the waterlogged landscape. The vast forests that were spreading across the former deserts created entirely new ecological niches. There were opportunities for creatures that could climb trees, swim through swamps, or hunt in dense undergrowth. The dinosaurs, with their upright posture and efficient metabolism, were perfectly positioned to exploit these new environments. The diversification was explosive. Within just a few million years, dinosaurs had spread across the globe and evolved into dozens of different forms. There were tiny insectivores no bigger than chickens, long-necked browsers that could reach high into the primitive conifers, and early predators with razor-sharp teeth. Each new ecosystem created by the Great Rain spawned new dinosaur species, adapted to exploit its unique resources. But dinosaurs weren't the only winners in this biological lottery. The Carnian pluvial episode marked the emergence of many groups that would go on to dominate later ecosystems. The first true mammals appeared during this time, tiny shrew-like creatures that scurried through the undergrowth of the new forests. Turtles emerged, their shells providing protection, in a world that was becoming increasingly dangerous as new predators evolved. Crocodiles made their debut during the Carnian pluvial episode. though these early crocodilians looked nothing like their modern descendants. Some were fully terrestrial, running on long legs across the mudflats of the transformed landscape. Others were already taking to the water, beginning the evolutionary journey that would make them the supreme aquatic predators of the Mesozoic. Perhaps most remarkably, this was also when the ancestors of modern lizards and snakes first appeared. The lepidosaurs, as paleontologists call this group, were tiny creatures during the Carnian pluvial episode, but they carried within their genes the potential for incredible future diversity. They would eventually give rise to everything from massive marine reptiles to venomous snakes to the tuatara, a living fossil that still survives in New Zealand today. The transformation wasn't limited to animals. The plant kingdom was undergoing its own revolution, driven by the abundance of water and nutrients washing off the continents. For the first time since the Great Permian extinction had ended the Paleozoic era, coal swamps began to form again. Vast peat bogs accumulated in the lowlands, fed by the constant decay of ferns and early conifers. These weren't the coal swamps of the Carboniferous period, with their towering lycopsid trees and primitive amphibians. These were something new, dominated by conifers and cycads, plants that would define Mesozoic landscapes for the next 150 million years. The formation of these coal deposits marked the end of what geologists call the coal gap, a period of nearly 15 million years when virtually no coal formed anywhere on Earth. The re-establishment of coal-forming environments was crucial for the planet's future climate stability. Coal formation is essentially a way of removing carbon dioxide from the atmosphere and storing it underground. As the great swamp forests of the Carnian pluvial episode grew and died and were buried under sediment, they were pulling vast quantities of greenhouse gases out of the air, helping to moderate the extreme temperatures that the volcanic eruptions had created. But the most visible sign of transformation was the appearance of amber in the fossil record. Tree resin, the precursor to amber, forms when plants are under stress, typically from disease, injury, or environmental pressure. The fact that amber deposits first become common during the Carnian pluvial episode tells us that even the plants that were thriving were struggling to adapt to the rapidly changing conditions. Inside these ancient amber deposits, paleontologists have found some of the earliest examples of modern insect groups. Ants, beetles, and primitive flies are all preserved in exquisite detail, their bodies frozen in time as they went about their daily lives in the primordial forests. These insects were the hidden architects of the new ecosystems, pollinating plants, decomposing organic matter, and forming the base of food webs that would support larger animals. The marine revolution was equally dramatic. The chemistry of the oceans was changing in ways that favoured entirely new types of organisms. For the first time, scleractinian corals, the group that builds modern coral reefs, began to flourish. These weren't the first corals in Earth's history, but they were the first to form the kind of massive reef systems that we associate with tropical seas today. The secret to their success lay in a partnership that was forged during the chaos of the Carnian pluvial episode. The new dinoflagellates that had appeared in the plankton weren't just free-floating organisms. Some species had evolved the ability to live inside coral tissues, providing their hosts with nutrients through photosynthesis. This symbiotic relationship allowed corals to build massive skeletons of calcium carbonate, creating underwater cities that became oases of diversity in the changing seas. The timing wasn't coincidental. The massive inputs of nutrients from the continents, carried by the unprecedented river systems created by the Great Rain, provided the raw materials that both corals and their symbiotic partners needed to thrive. The slightly acidic conditions created by volcanic emissions actually favoured the precipitation of calcium carbonate, making it easier for corals to build their skeletons. These early reef systems bore little resemblance to modern coral reefs. They were dominated by massive dome-shaped corals that grew slowly in the murky, nutrient-rich waters. The diversity was lower than in modern reefs, but the sheer biomass was enormous. Entire shallow seas became paved with coral, creating underwater landscapes that would persist for millions of years. The success of the new reef systems had cascading effects throughout marine ecosystems. Fish populations exploded, taking advantage of the shelter and abundant food provided by the coral cities. New types of marine reptile appeared, some of them early experiments in the body plans that would eventually produce plesiosaurs and ichthyosaurs. The oceans were becoming more complex and more dangerous, but also more productive than they had been for millions of years. Yet even as life was diversifying and thriving in ways never before seen, the planet remained locked in cycles of environmental stress. The volcanic eruptions that had triggered the Carnian pluvial episode weren't a single event, but a series of pulses that continued for nearly 2 million years. Each new eruption brought fresh waves of greenhouse gases, triggering renewed climate instability. The pattern was relentless. Periods of extreme rainfall would be followed by droughts, but these weren't the same kind of droughts that had characterized pre-Carnian Pangaea. The landscape had been fundamentally altered. Even during dry periods, vast river systems continued to flow, fed by groundwater and the gradual release of moisture from the transformed vegetation. Lakes that had formed during the wettest periods became permanent features, creating stepping stones for life to spread across the continents. This environmental instability was actually driving evolution at an unprecedented pace. Species that could adapt quickly to changing conditions had enormous advantages over those that couldn't. Natural selection was operating on overdrive, favoring traits like behavioral flexibility, rapid reproduction, and efficient metabolism. The result was an evolutionary arms race that accelerated the pace of biological innovation. The consequences reached far beyond the Triassic period. Many of the fundamental patterns that would characterize life for the rest of the Mesozoic era were established during the Carnian pluvial episode. The dominance of dinosaurs, the modern style of marine ecosystems, the conifer-dominated forests, even the basic architecture of terrestrial food webs, all trace their origins back to this period of global transformation. As the second million years of the Great Rain drew to a close, the planet that emerged was almost unrecognizable from the one that had existed before. Where once there had been endless desert, now there were forests, lakes, and rivers. Where once life had clung to narrow coastal refugia, now it spread across entire continents. The age of dinosaurs had truly begun, and with it, a new chapter in the story of life on Earth that would continue for the next 150 million years. 50 million years. The transformation was irreversible. By the time the last of the great rains finally ceased, Earth had crossed a threshold from which there could be no return. The planet that emerged from this 2 million year deluge was not simply a wetter version of the desert world that had come before. It was an entirely different world, operating under new rules, governed by new cycles, and dominated by new forms of life. The most profound change was invisible, but fundamental. The carbon cycle, that great planetary breathing system that regulates Earth's temperature and atmospheric composition, had been completely rewired. For millions of years before the Carnian pluvial episode, carbon had been locked away in rocks and sediments, unable to participate in the dynamic exchanges between atmosphere, oceans, and life. The Great Rain had changed all that. The massive erosion caused by unprecedented rainfall had liberated vast quantities of carbon from ancient rocks, washing it into the oceans where it could once again become part of living systems. At the same time, The new forests and swamps were pulling carbon dioxide out of the atmosphere at rates never before seen in Earth's history. The planet was learning to breathe again, establishing the rhythms of carbon exchange that would sustain complex ecosystems for hundreds of millions of years. But perhaps the most remarkable aspect of this transformation was how quickly the planet's systems adapted to their new configuration. Within just a few 100,000 years after the volcanic eruption subsided, the extreme swings between flood and drought began to moderate. The vast forests that now covered much of Pangaea were acting as enormous sponges, absorbing excess rainfall during wet periods and releasing it slowly during dry ones. The climate was becoming more stable, more predictable, more suitable for complex life. This stability allowed the evolutionary experiments begun during the chaos of the Carnian pluvial episode to mature and diversify. Dinosaurs, no longer small opportunists hiding in the shadows, began to grow larger and more specialized. The first giant dinosaurs appeared, long-necked sauropods that could browse on the crowns of the new conifer forests. Predators evolved to hunt them, developing the massive jaws and razor teeth that would make dinosaurs the apex predators of their age. The success of these early dinosaur communities created a feedback loop that would define terrestrial ecosystems for the next 150 million years. As dinosaurs grew larger and more diverse, they began to modify their environments in ways that favored even more dinosaur diversity. Their trampling created clearings in dense forests, their feeding habits spread seeds across vast distances, and their waste products enriched soils in ways that promoted plant growth. In the oceans, the new reef ecosystems were becoming architectural marvels that rivaled anything built by modern corals. These underwater cities stretched for hundreds of miles along the coasts of Pangaea, creating barriers between the open ocean and shallow lagoons. Behind these barriers, new types of marine environments evolved, from crystal-clear lagoons perfect for filter-feeding organisms to murky back reef areas rich in organic matter. The complexity of these marine systems was staggering. Each reef supported hundreds of species of fish, mollusks, arthropods, and other marine life. The relationships between these organisms were intricate beyond imagination, with elaborate food webs connecting everything from microscopic plankton to massive marine reptiles. The oceans had become true ecosystems for the first time, not just collections of individual organisms struggling for survival. If you could float above this world, watching from the quiet safety of the orbit, you would see coastlines glowing with living light. During the day, vast reef systems traced the margins of continents in broken necklaces of pale stone and turquoise water. At night, the surface turned black, but just beneath it, the reefs pulsed with the faint, eerie shimmer of bioluminescent plankton and strange, glowing organisms that had evolved to exploit the darkness. The Carnian seas were no longer just water and chemistry. They were busy, crowded, layered worlds. From that distant vantage point, something else would stand out as well. You would see clouds, enormous, spiraling storm systems that wrapped around the planet like ghostly bands. You would see rivers, now permanent scars of silver across Pangaea's red-brown surface, and inland lakes that glittered like newly opened eyes. The 2-million-year rain had not simply added water to a dry planet. It had reorganized the entire surface of Earth into new pathways for energy and life. If you could descend through those clouds, down past the roaring upper winds and the endless sheets of rain, and walk along one of those new rivers, you would find a world in the middle of reinvention. Along the floodplains, the soil would be dark and rich, churned constantly by cycles of inundation and retreat. Seed ferns and conifers crowded every patch of available ground, their roots reaching greedily into newly formed sediment. In some places, shallow pools left behind by receding floods would shimmer with a green film of algae, the first step in building yet another layer of the food web. In others, the water would be stained brown with tannins from rotting vegetation, quietly accumulating the raw material that would, millions of years later, harden into coal seams deep beneath your feet. And everywhere you looked, there would be tracks. Not just dinosaur tracks. Their three-toed imprints were important, yes. Evidence of a future that hadn't yet unfolded. But they were only part of a greater pattern. There would be the drag marks of early turtles hauling themselves from water to land, the delicate toe prints of tiny lizard ancestors skittering between roots, the broad, rounded impressions of early mammal relatives pressing their bodies low to the ground as they moved from burrow to cover. This was not a stable, settled ecosystem. It was a workshop. The planet was experimenting. In those experiments, size was no guarantee of success. Some of the largest animals of the pre-rain world were now ghosts, their lineages broken, their bodies preserved only as fragments in the new mudstones. Meanwhile, creatures that could hide easily, reproduce quickly, and shift their behavior from one year to the next had enormous advantages. One year the forest might be a saturated swamp, its floor submerged beneath knee-deep water. The next, the rain might retreat, leaving behind a maze of drying pools and thick, humid air. In such a world, the ability to wait, to sleep, to burrow into mud and emerge when conditions were right, was just as powerful as claws or armor. Among the early mammals, this strategy became a way of life. These tiny furred creatures, still bearing many reptilian features, learned to make their homes underground and under roots. They came out to feed when temperatures dropped and when larger predators were distracted. Their bodies ran warmer than the reptiles around them, giving them a slight edge in cool nights and sudden weather swings. Lightning might split the sky. Rivers might burst their banks. Forests might die and regrow, but as long as there were insects to eat and dark spaces to hide, these early mammals endured. As the rain worked its way into every ecological niche, it also infiltrated the rocks themselves. The same water that fed forests and rivers seeped down through cracks and pores in the crust, altering minerals, dissolving some, expanding others. The continents were literally swelling with moisture, their outer skin transforming grain by grain. The white, chalky limestone of ancient seas was being overlaid by darker, clay-rich layers. The red desert sandstones were capped with grey and brown deposits full of plant material and mud. Millions of years later, this vertical story in stone would become the key to reconstructing what had happened. To the animals and plants living through it, it was just the ground underfoot. Yet even as life adapted to this wet, unstable world, the engines driving the change continued to shift gears. The volcanic fields of Rangelia did not erupt continuously, like a single, endless fountain of lava. Instead, they pulsed. Great outpourings of basaltic magma would bury landscapes under glowing rivers of rock. Then quiet would return for thousands or tens of thousands of years. During those pauses, ecosystems tried to catch their breath, reorganizing themselves around new coastlines and cratered plateaus still steaming with residual heat. Then another pulse would come, releasing another wave of gases and ash, recharging the greenhouse and the rain. You can think of the Carnian pluvial episode as a kind of planetary heartbeat, a long, irregular but persistent rhythm of disturbance and recovery. Each beat shook the climate, reshuffled habitats, and applied fresh pressure to the evolving tapestry of life. In the oceans, that heartbeat left echoes in the chemistry of seafloor sediments. If you sliced a drill core from the ancient seafloor and laid it out in front of you, you would see repeating bands of colour and texture. Pale layers full of coccolith shells and tiny fossils would alternate with darker organic rich layers, telling of oxygen-poor depths. Each transition marked not just a change in climate, but a shift in who ruled those waters. Plankton blooms rising and collapsing, reefs expanding and retracting, predators following their prey into new territories. In some intervals, the sediments would be streaked with thin horizons of volcanic ash, delicate glass shards and crystals silently recording individual eruptions. These were the fingerprints of the Rangelia pulses, deposited far from their source by global wind currents and falling gently onto the ocean surface before sinking to the bottom. They were, in a sense, timestamps, a way of saying, here, at this depth, the sky once turned dark and the sun dimmed. Above those ash layers, the fossils often changed. Certain species vanished, never to return. Others appeared suddenly, as if conjured out of nowhere, their ancestors still unknown to us. Some, like the early reef-building corals, simply thinned and then thickened again, riding out the swings. From the perspective of a single organism, these changes were catastrophic or fortunate, matters of life and extinction. From the perspective of the planet, they were rearrangements of possibilities. Back on land, the rearrangements could be seen in the bones. In the Dolomites, those dinosaur footprints were only one part of the story. Elsewhere, in South America, in what is now Argentina, fossil beds preserve the bodies of some of the earliest true dinosaurs whose skeletons we can study in detail. Names like Herrerasaurus and Dioraptor, small by later dinosaur standards, but already carrying the hallmarks of the group: upright posture, powerful hind limbs, lightweight bones. When paleontologists traced the layers in which these animals appeared, they kept encountering the same pattern. Below a certain level, the rocks were dominated by different types of reptiles: large-bodied herbivores with sprawling gaits, thick-skulled predators with deep, heavy jaws. Above that level, many of those forms dwindled, and dinosaurs appeared in their place, sometimes in startling abundance. It is tempting to imagine the change as an invasion, dinosaurs pouring in from distant lands, pushing out the residents and claiming their territory. The reality was subtler and more drawn out. In many regions, dinosaurs had been present all along, small and overlooked. The rain did not bring them to the stage. It cleared space on the stage and then offered them new props. In a world of constant flooding, being light on your feet mattered. Upright posture allowed faster running across mud and shallow water. Limb bones held closer to the body were less likely to be trapped in sticky sediment. Efficient lungs and active metabolisms allowed long-distance travel when local conditions worsened. As forests expanded, creatures that could rear up, see over vegetation, or move quickly through dense undergrowth had the advantage. Again and again, in ecosystem after ecosystem, the same traits rose to the top, and so did the creatures that carried them. If you pause here, at this moment in deep time, and look forward along the timeline of Earth, you can trace a direct line from those rain-soaked floodplains to the later giants of the Jurassic and Cretaceous, the long-necked sauropods, the armor-plated stegosaurs and ankylosaurs, the toothy tyrannosaurs and sleek bird-like raptors. The genetic toolkit that would eventually produce all those forms was being refined right here, under clouds that never seem to empty. But this is not just a dinosaur story. The rain was rewriting more than bones. High in the atmosphere, new patterns were emerging. Before the Carnian pluvial episode, global circulation has been dominated by the vast, unbroken interior of Pangaea. Huge high-pressure cells sat over the desert heart of the supercontinent. driving dry winds outward in all directions. Moisture from the oceans rarely penetrated far inland. Weather systems formed and dissipated along narrow coastal bands. As the rain fell and forests spread, those patterns changed. The dark, vegetated surface of new woodlands absorbed more sunlight than bare rock and sand, heating the air above them differently. Evapotranspiration, the combined release of water vapor from soil and plant leaves, fed towering clouds that reached high into the troposphere. These clouds, in turn, altered where and how the atmosphere released its energy. From space, storm tracks shifted. Monsoon-like systems developed along new east-west bands, following the outlines of emerging mountain ranges and the positions of inland seas. The atmosphere had discovered new ways to move heat from equator to poles, new routes along which to carry moisture. It was as if the planet had discovered a different way to spin. Deep underground, the plates themselves continued their slow tectonic dance. Although Pangaea still held together, stress built along its seams. Basins sagged, mountains rose, coastlines flexed. In some places, these tectonic changes created basins that were perfectly positioned to capture the runoff of the great rain, becoming long-lived lakes or inland seas. In others, uplifted regions escaped the worst of the flooding, becoming refuge zones for species that could not cope with the new wetlands. The interplay between rain, erosion, and tectonic uplift produced feedback loops of staggering complexity. Eroded sediments from uplifted areas filled nearby basins, changing water depths and shoreline positions, which in turn influenced local climate and vegetation. Vegetation stabilized slopes, modifying erosion rates. The system was not simple, it rarely is. Yet through all these intricacies, a broad direction emerged. More water stored on land, more diverse landscapes, more interconnected habitats. From the perspective of a future geologist tracing these changes in rock, the pattern is evident. From the perspective of a small animal living among the ferns, it would have felt like chaos. Imagine one of those early mammal ancestors, no larger than a modern rat navigating this world. In one generation, the familiar patch of forest might be swept away by an expanding river. In another, a new stand of conifers might grow where there was once open ground, changing the predators that hunted there. Perhaps a nearby lake, reliable for many breeding seasons, suddenly rises and floods burrows, forcing a frantic search for new shelter. Perhaps a new kind of insect appears in large numbers, offering a rich new food source, if you can figure out how to exploit it. Natural selection is not a deliberate process. It has no foresight. But in environments like this, it has plenty of raw material to work with. Each generation experiences the world slightly differently than the last. Each small mutation, each behavioral quirk, each new combination of traits interacts with the shifting terrain in ways that can either open doors or close them. The Carnian pluvial episode was, in essence, a 2-million-year series of open doors and slamming gates. Eventually, slowly, the gates stopped moving so violently as volcanic activity tapered off and the atmospheric burden of greenhouse gases began to ease. Helped along by all those new forests and swamps, the climate system settled into a new regime. Rain still fell, rivers still flowed, forests still grew. But the extreme oscillations between flood and drought softened. Seasons became more predictable. Regional climates differentiated. Some areas remained humid and warm, others trended back toward aridity, but none returned entirely to the old global desert state. For the life that had passed through the crucible, this increasing stability was a chance to refine and specialize. Dinosaurs that had started as generalists, able to cope with a wide range of conditions, began to diverge into narrower roles. In wetter regions, some lineages took to swampy forests, becoming semi-aquatic or thick-limbed marsh dwellers. In drier uplands, others evolved into swift, lightly built runners adapted for open terrain. Herbivores lengthened their necks to reach different layers of foliage. Predators refined their claws and teeth for particular types of prey. Plants, too, diversified along climatic gradients. In certain areas, conifer forests grew tall and dense, their needle-like leaves reducing water loss and allowing survival through periodic dry spells. In others, seed ferns and cycads dominated, their broad fronds catching what light they could under heavy cloud cover. New symbioses formed between plants and fungi, plants and insects, plants and the microbes in their root zones, each partnership increasing the resilience of the ecosystems that hosted them. By the time the last of the Carnian rains faded into a more ordinary Triassic climate, the world was no longer in transition. It had arrived somewhere new, and the rocks remembered. Those dark, clay-rich layers in the Alps in England and Utah, those coal seams and kaolinite deposits and fossil river channels, became pages in a book written in minerals and time. For millions upon millions of years, they lay buried, compressed, folded by tectonics, lifted high into mountains, carved again by new rivers and new cycles of ice and thaw. When Wolfgang Schlager and Matthias Schollenberger walked those Austrian slopes in 1975, they were not just looking at stone. They were looking at the petrified remains of storms that had fallen on trees and rivers and small scurrying animals nearly 250 million years before. At first, all they saw was a puzzle. A dark band where there should have been none, a chemical signature that did not belong. It took decades, and contributions from dozens, then hundreds, of other researchers scattered around the world for the pattern to come into focus. Each new outcrop studied, each core drilled, each fossil catalogued added another pixel to the image. Eventually the picture sharpened, not a brief anomaly, but a planet-wide transformation. When you zoom out far enough, the Carnian pluvial episode becomes one of several such transformations threaded through Earth's history. There were earlier crises, earlier pulses of volcanic activity and climate chaos. The Permian extinction, just a few million years before the Great Rain, had nearly wiped out complex life. There would later be others, the Triassic, the Cretaceous, the Paleocene-Eocene thermal maximum. Each had its own triggers, its own tempo, its own winners and losers. What makes the 2-million-year reign unique is not merely its cause, but its outcome. It did not simply prune the tree of life. It reshaped the soil in which that tree grows. It rewired carbon cycles, established new plant communities, and seeded the world with lineages that would dominate for ages. It gave us forests and reefs and dinosaurs, yes, but it also set the stage for everything that would come after the dinosaurs were gone. For mammals to rise, for birds to spread, for flowering plants to rewrite landscapes again. In a sense, we're all living in the long shadow of that rain. If you lie awake at night and listen to a storm tapping against your window, it is hard to imagine a world in which that sound never stops. Harder still to imagine that such unending water could be anything but destructive. And yet, on deep timescales, catastrophe and creation are often the same event viewed from different distances. For the animals drowning in sudden floods, the Carnian rains were the end. For the seeds carried downstream into new valleys, they were the beginning of a forest. For the reptiles that could not cope with soggy plains, the constant storms were a slow execution. For the small, fast, warm-blooded creatures learning to thrive in the undergrowth, they were a doorway into the future. For us standing on the far side of hundreds of millions of years, they are a reminder a reminder that climate is not a backdrop, but a character in the story of life, that environments can change not only gradually, but abruptly and comprehensively, that the boundaries between crisis and opportunity are fluid, defined as much by biology as by physics. It is also a reminder of how much of that story is still buried. Even today, new evidence of the Carnian pluvial episode is emerging from places no one had thought to look. Drill cores from deep beneath the Pacific, mudstones weathering out of remote canyon walls, chemical signatures locked in tiny mineral grains that can be analysed only with the most precise instruments. Each new data point tightens the constraints on our reconstructions, sharpens the contours of storms that have been over for 230 million years. Meanwhile, the very concept of the 2 million-year rain is being refined. Geologists now suspect that the Carnian pluvial episode was composed of several shorter pulses, each a few 100,000 years long, separated by intervals of relative calm. The Great Rain was not a uniform curtain of water, but a symphony with loud and quiet movements. Some phases brought overwhelming humidity and flooded continents, others brought only intensified seasonal cycles. Different regions experienced the event differently, depending on their latitude, altitude, and distance from volcanic centers. For creatures living through it, of course, the subtleties did not matter. Wet was wet, flooded was flooded. From our vantage point, however, those nuances help explain the patchiness of the fossil record. They help us understand why some areas show pronounced environmental shifts, while others appear more muted. They remind us that even the most global of events are expressed locally, filtered through the geography and biology of particular places. If you close your eyes now and imagine yourself back in that time, standing on a high ridge of newly deposited sediment, you might see something like this. To one side, a vast lowland stretches toward a hazy horizon, patterned with braided rivers that glimmer dully under heavy clouds. The air smells of wet stone and resin from conifers. In the distance, lightning flickers, but the thunder is swallowed by the constant hiss of falling rain. Below you, in a shallow depression, a herd of small bipedal herbivorous dinosaurs is moving cautiously between stands of tree ferns, their heads held high, listening for predators. Their skin is mottled in muted greens and browns, slick with moisture. Occasionally one pauses to scratch the bark of a conifer with its beak, stripping away a strip of soft tissue. Their tracks crisscross the mud, overlapping with the prints of earlier visits. A little farther downslope, the earth falls away into a ravine carved recently by flash floods. Its walls are raw, streaked with alternating layers of red desert sandstone and newly deposited grey mudstone. Here and there, the jutting ends of older root systems stick out, torn away from trees that once grew above. At the bottom of the ravine, a torrent of brown water surges past, carrying branches, leaves, and the occasional carcass. Above you, high on the skyline, the outline of a volcano smoulders, trailing a faint plume into the cloud deck. It is quiet for now, but the ground under your feet carries a faint tremor, a reminder that deep below, molten rock still moves, still seeks new paths to the surface. The world is restless, but it is not empty. It is busy, messy, alive. Millions of nights like this would pass before the Carnian pluvial episode finally faded into memory. Most of the creatures that lived under those rains would never know that they were part of something extraordinary. They were just trying to find food, avoid predators, raise offspring, and endure the next storm. We are the ones who get to name the event, to see it as a coherent whole, to draw boundaries on a timescale chart and say, here, for 2 million years, the sky broke. And yet, even with all our charts and reconstructions, there is still more hidden in those layers than we can read. Somewhere in the coal seams formed from those ancient swamps, there may be traces of plant lineages we've never discovered, their leaves and spores preserved only as smudges. Somewhere in the mudstone beds of a forgotten basin, there might be the bones of a dinosaur that experimented with a body plan that led nowhere. Somewhere in the chemical ratios of a single mineral grain, there might be a record of a brief, sharp, cooling episode that momentarily silenced the rain. Deep Time is not a finished book. It is a palimpsest, endlessly overwritten but never entirely erased. As you lie here listening to this story, perhaps with the gentle patter of modern rain outside your window, or only the soft hum of distant traffic, the difference between your world and that ancient one might feel absolute. We have cities, satellites, electricity, complex societies. They had ferns, lava flows, and small reptiles trying to outrun floods. Yet at the level of physics and chemistry, the rules have not changed. Greenhouse gases still trap heat. Volcanic eruptions still inject particles into the stratosphere. Forests still recycle water and carbon. Oceans still absorb, store, and redistribute energy. When those systems are pushed hard enough, they still respond, not gently, but with sudden shifts, tipping points, cascades. The Carnian pluvial episode is, among many other things, a case study in how profoundly and how quickly those responses can reshape the biosphere. But our story is not finished. The end of the 2-million-year reign was not the end of Earth's climate experiments, nor the end of the line for the creatures whose fortunes it had raised or destroyed. It was rather the beginning of a new equilibrium on which future disruptions would be layered. In the layers of rock above the Carnian mudstones, another drama is waiting. New volcanic provinces, new pulses of extinction, new opportunities for life to reinvent itself, and in those higher strata, the world that seems so distant to you now will slowly, step by step, become more recognizable. The continents will begin to split apart, the Atlantic will open, the climates of high latitudes will cool and warm and cool again, dinosaurs will reach unheard of sizes and then, one day, vanish. Mammals will step into the empty spaces they leave. Flowers will spread. Grasses will knit together plains. Ice sheets will advance and retreat over northern lands. Primates will emerge in forests. Then some will leave the trees and learn to walk upright on open ground. The rains will come and go, season after season, epoch after epoch. But for now we remain in that Carnian night, listening to a storm that has lasted for 1,000,000 years already, and will last for another 1,000,000 more, watching as the world beneath it continues to transform in ways that will echo deep into the future. If you stand in that ancient landscape a little longer, the details begin to sharpen. The rain does not fall evenly everywhere. Over low coastal plains it comes in steady curtains, a monotone roar that rarely changes. But over the uplands and new mountain chains, it arrives in convulsions. Storm cells build like black fortresses, towering 15 or 20 kilometers high, their tops spreading into anvils that glow faintly from within as lightning forks through them. When these storms break, they do not simply wet the ground. They rearrange it. One of these mountains rises in what will one day be western North America. At its peaks, thin conifer forests cling to scree slopes, their roots gripping shattered rock. The soil is shallow, barely more than a skin. When the first sheets of rain strike, they loosen grains of sand and chips of stone. As the storm intensifies, the water can no longer soak in. It begins to move downslope, first as films, then as rivulets, then as torrents. Within an hour, entire hillsides are on the move. Mud flows pour into valley bottoms, burying old stream channels under new layers of sediment. Rocks tumble, colliding and shattering, turning into pebbles, then into gravel and sand. Trees, uprooted and carried along, become rams battering anything in their path. Somewhere down valley, a herd of herbivorous reptiles is caught in the rush. Their bodies are engulfed and entombed, each one becoming a future fossil, an unwitting witness sealed into the narrative of the storm. As the rain finally slackens, the flow begins to sort itself. Coarse boulders come to rest first, then smaller rocks, then sand, then silt. A new deposit has formed, a fan-shaped wedge of debris that spreads into a basin, raising the valley floor by several meters. The next time it floods, the river will take a slightly different course. Over thousands of years, these subtle shifts will reshape the entire drainage network. This process plays out again and again, all across Pangaea, in basins and uplands, along new coasts and ancient interiors. Each event is local, but together they form a global pattern of accelerated erosion. Whole mountain ranges are being lowered, grain by grain, and their material is being transported into oceans that are hungry for it. When modern geologists study these ancient deposits, they see evidence of this violence in the shapes of the grains. Under a microscope, crystals of feldspar and quartz are chipped and angular, telling stories of rapid transport and little time for smoothing. Fragments of volcanic rock are mixed with older, more stable minerals. Bits of plant material are trapped between grains, compressed but still recognizable. The rocks are not random, they are archives. Deep beneath what is now China, similar archives were forming during the Carnian pluvial episode. There, entire lake systems swelled and contracted with each climatic pulse. In wet phases they spilled over their banks, forming satellite lakes and wetlands. In dry phases they retreated, leaving behind flats of cracking mud patterned like scales on a reptile's back. For animals tied to the water, amphibians, early aquatic reptiles, freshwater fish, each swing was a test. Some of those tests favoured innovation. In one lake, a population of fish begins to explore marginal habitats. When water levels drop, they move into shallow, warm pools crowded with plants. Oxygen levels are low there, but the fish have slightly more efficient gills than their neighbours. Over generations, this small advantage becomes amplified. The fish that can tolerate the worst conditions survive and breed. Those that cannot disappear. Slowly, a lineage emerges that can cope with fluctuating oxygen levels, with sudden heat, with shifts in water chemistry. That lineage will eventually give rise to forms capable of colonizing almost any freshwater ecosystem the planet can produce. Elsewhere along the shore, amphibians experiment in their own way. Some remain wedded to the water, laying strings of jelly-covered eggs in sheltered shallows. Others begin to seek sites farther upslope, digging shallow nests that hold just enough moisture to keep eggs from drying out. They're clumsy pioneers of more independent reproduction. But in a world where ponds can evaporate in a season, their awkward experiments sometimes succeed where traditional strategies fail. The rain, indifferent, simply continues to fall. If you follow one of the swollen rivers downstream, you eventually reach the margins of an inland sea that did not exist before the Carnian pluvial episode. It is broad and shallow, its waters turbid with sediment. Here, wave energy is low enough for mud to settle out in fine layers. Each rainy season lays down a new film of silt and clay. Each dry season adds wind-blown dust, ash, and the remains of plants and animals that died along the shore. Viewed from above, the shoreline is intricate and fractal, cutting deeply into the surrounding land. Bays become nurseries. Narrow inlets trap nutrients. Sandbars form, are breached, and reform, creating a constantly shifting mosaic of habitats. Wading reptiles hunt in the shallows. Fish dart between submerged logs. In the quieter corners, thick mats of algae and primitive moss-like plants trap and bind the sediments, forming the beginnings of peat deposits that will later become coal. At this scale, the planet feels impossibly complex. Tens of thousands of microhabitats, each with its own rules. But the broad strokes can still be seen. Temperatures, though high by modern standards, are not uniform. Near the equator, the combination of intense sun, high humidity, and constant cloud cover creates a greenhouse climate reminiscent of a hothouse greenhouse cranked too high. Toward the poles, where Pangaea reaches into cooler latitudes, conditions are milder. There, the Carnian rains fall as persistent drizzle rather than violent downpour. Forests are denser, and some regions may even experience seasonal cold. In these higher latitude refuges, certain plant lineages find opportunities that the equatorial zones cannot offer. Some conifers evolve tighter cones and denser wood, traits that help them withstand occasional frost. Ferns experiment with different leaf shapes to catch limited sunlight. The insects that accompany these plants likewise diversify, developing new mouthparts and life cycles tuned to the rhythms of shortening days and lengthening nights. Millions of years later, when paleobotanists study fossil leaves from these regions, they will notice the first subtle hints of what we now think of as modern forest ecology. Layered canopies, specialized understory plants, complex pollen profiles. The template of a temperate forest is being sketched faintly in the margins of a superheated world. Meanwhile, the interior of Pangaea is learning a different lesson. No amount of rain can fully erase the legacy of a continent so vast. Some areas, shielded by mountains and far from moisture sources, remain semi-arid even during the peaks of the Carnian pluvial episode. There, the landscape shifts between scrubby woodland and open steppe, dotted with scattered trees and low, hardy plants. In these transitional zones, animals must walk a fine line. Too specialized for wet conditions, and they cannot survive the inevitable dry spells. Too specialized for dryness, and they are outcompeted when brief wet intervals bring lush growth. It is in these uneasy ecotones that some of the most resilient lineages emerge. A small bipedal omnivore, distant kin to the more strictly herbivorous dinosaurs of the swampy lowlands, ranges through these open woodlands. Its teeth are not specialized for any single type of food. It can nibble young shoots, snap up insects, scavenge carcasses, and raid nests. It does not excel at any one task, but it is rarely completely without options. In years when the rains are late and plant growth is stunted, it leans on animals. In years when the storms are generous, it fills its gut with vegetation. Over time, such generalists become the backbone of ecosystems. They bridge energy pathways, connect plant-based and animal-based food webs, and stabilize fluctuations. When specialists fail, generalists persist. The Great Rain favors them, even as it opens niches for more delicate experiments. If we step away from the biological details and return to the quiet work of the rocks, another layer of the story comes into focus. Inside certain minerals, atoms of oxygen are locked into crystalline lattices. Some of these oxygen atoms are slightly heavier than others. They carry extra neutrons. The ratio between heavy and light oxygen isotopes, as they are called, depends on the conditions under which the minerals formed, especially temperature and the composition of the water from which they grew. When geochemists extract these minerals from Carnian Age rocks today and measure those ratios with painstaking care, they reconstruct ancient temperatures and rainfall patterns. The results confirm what the field evidence already suggests: not just a simple warming, but a world of exaggerated extremes, Periods of intense warmth and humidity alternate with more moderate intervals. Regional climates oscillate in step with the pulses of volcanic activity and the slow breathing of the carbon cycle. In some places, the oxygen isotope record hints at brief, sharp cooling events superimposed on the overall warmth. Perhaps moments when volcanic ash clouds temporarily blocked sunlight, or when changes in ocean currents redistributed heat differently. For life on the ground, these deviations may have meant harder winters, altered growing seasons, or sudden shifts in the timing of rains. Think of a plant whose seeds are tuned to sprout after the first heavy storms of the season. If those storms arrive late, seedlings may not have enough time to mature and reproduce before conditions become harsh again. A single mistimed year can reduce population sizes. Several in a row can drive a species to the brink. Natural selection, relentless and quiet, sifts through these challenges, favouring lineages that are either flexible or remarkably well matched to the new regime. While Earth is absorbed in these deep rearrangements, the skies above host another form of life that rarely fossilizes but leaves subtle traces. The first true flying reptiles. Pterosaurs make their debut around this time, emerging from small, agile archosaurs that began by leaping between branches and gliding down from heights. In a world broken into countless lakes, rivers, and lagoons, and where forests press close to the water's edge, the ability to move quickly through the air is a powerful advantage. Insects whirl in great swarms over backwaters. Small fish flash near the surface. Carcasses wash up along muddy shores and sandbars. The earliest pterosaurs are not the enormous sky lords of the later Mesozoic. They are modest in size, with wingspans measured in tens of centimetres. Their bones are hollow and delicate, their muscles are strong. They clamber up tree trunks, launch into humid air with quick, flapping beats, and circle above water and forest looking for opportunities. The rain, which to ground-bound creatures is an obstacle or a threat, becomes to them a shifting texture in the air. They learn to ride the gusts that race ahead of storm fronts, to navigate the turbulent boundary between downdraft and updraft. When lightning flashes, they fold their wings and cling to trunks, riding out the worst of it. When storms pass, they are among the first to move into freshly altered landscapes, scavenging and exploring. Their presence adds a new dimension to ecosystems. Predators are no longer confined to earth and water. Danger can arrive from above. Small vertebrates must learn to watch the sky as well as the undergrowth. Insects face new pressures that will, over time, influence their flight patterns, their body shapes, their behaviour. Once again, the rain is not simply water, it is context. It shapes what kinds of bodies and strategies are possible. Beneath the oceans, similar experiments are unfolding in the realm of marine reptiles. The proto-ichthyosaurs and other early marine reptiles that survived earlier Triassic crises find in the new Carnian seas a buffet of possibilities. With reefs expanding, fish diversifying, and invertebrate communities flourishing, there is no shortage of food. Some lineages streamline their bodies, becoming faster, more efficient swimmers, capable of pursuing agile prey. Others grow heavier heads and crushing jaws, adapting to crack shells and crush armoured creatures, hiding among coral branches and seafloor sediments. In one lineage, subtle changes in limb bones, from robust, weight-bearing structures to more flattened, paddle-like forms, mark the progression from shore-hugging habits to fully pelagic life. At first, these reptiles need to haul themselves onto land to lay eggs. Later, they evolve the ability to give birth in water, freeing them entirely from shorelines. Fossilized skeletons of pregnant individuals discovered millions of years later capture this intimate biographical detail. All of this is happening while rains continue to feed rivers that deliver nutrients to the seas. It is happening while volcanoes wax and wane, while forests advance and retreat, while continents slowly stretch and crack. From the vantage point of a single human lifetime, the Carnian pluvial episode would look impossibly slow, the landscape changing only gradually. From the vantage point of geological time, it is a flurry, a concentrated burst of rearrangement in which the planet tries many possibilities in rapid succession. Slowly, almost imperceptibly, the frequency and intensity of storms begin to ease. The volcanic centres lose some of their vigour. Lava still flows, ash still falls, but the great pulses that once shook climate systems grow more widely spaced. Forests, now well established, act as reservoirs for both water and carbon. They soften the edges of droughts by holding moisture in soils and trunks. They buffer floods by slowing runoff. They absorb and store carbon dioxide, damping the extremes of greenhouse warming. In some regions, peat bogs have grown so thick that their own weight causes them to sink, forming domed wetlands. Layers of partially decomposed plant material accumulate, each one a thin, soggy page in a story of atmospheric carbon being quietly withdrawn and archived underground. When these layers are later buried by sediments and heated, coal will form, not the towering seams of the Carboniferous, but significant deposits nonetheless. The formation of coal is not just a curiosity, it is a conveyor belt moving carbon from the air into deep time. With each gram locked away, the greenhouse curtain thins slightly. Over millions of years, such processes help bring Earth's climate into a new balance. Even so, the planet is not marching towards some predetermined endpoint. It is drifting, feeling its way, responding to feedbacks that amplify or mute certain changes. In one region, for reasons tied to local geography and circulation patterns, a relatively dry interval takes hold. Forests thin, giving way to more open, savanna-like communities of conifers and seed ferns. Grazing and browsing dinosaurs adapted to drier conditions move in, their bodies shaped for covering long distances between patches of greenery. Predators follow, lean-limbed and observant, using low vegetation as cover. In another region, perhaps a low-lying coastal plain fed by several large rivers, humidity remains high and rainfall frequent even as global patterns moderate. There, swamp forests deepen and waterlogged soils become thick with roots. Amphibians and semi-aquatic reptiles thrive. Insects adapted to stagnant water, early relatives of mosquitoes and dragonflies, multiply. Fish that can tolerate low oxygen prosper in backwaters. These pockets of persistent wetness act as reservoirs of diversity, sheltering lineages that might otherwise be squeezed out. Such regional differences matter because they create a patchwork of refugees and laboratories. When global conditions change again, as they inevitably will, the survivors will not be randomly scattered. They will be drawn disproportionately from those pockets where the right balance of stability and challenge allowed lineages to both persist and evolve. From our perspective, one of the most striking consequences of the Carnian pluvial episode is that by its end, the silhouette of the Mesozoic world is clearly visible. Look at a timeline of Earth history and mark the events. Before the Great Rain, ecosystems are still recovering from the apocalyptic end Permian extinction. Dominant groups are different, experimental, many of them carrying over Paleozoic legacies. After the Great Rain, the cast has changed. Dinosaurs, pterosaurs, early mammals, modern-style corals, conifer forests. These are no longer marginal figures. They are central, setting the tone for the next 150 million years. The rocks capture this shift in a subtle but telling way. In the disappearance of certain fossil types and the sudden abundance of others, in changes in sediment structures that reflect different root systems, in shifts in the chemical signatures of organic matter preserved in mudstones and shales. But the rocks do not tell us what it felt like to live through it. To approach that feeling, you have to imagine the sensory world of the time. Imagine the soundscape of a Carnian forest during a heavy storm. Rain hammers on leaves and needles, trickles down trunks, splashes into puddles. Branches creak under the weight of water and wind. Somewhere nearby, a large herbivorous dinosaur crashes through the undergrowth, its footsteps muffled but heavy. Distantly, the low growl of thunder rolls across the landscape, punctuated by sharp cracks of closer lightning. In between, there are the smaller sounds, the whir of insects' wings, the croak-like calls of amphibians, the splash of something slipping into a stream. The air is thick with smells, resin from damaged conifer bark, the sour tang of fermenting plant matter, the mineral scent of wet rock, the faint musk of animal bodies. Visibility is limited not only by vegetation but by mist. Everything feels close. For small creatures, this closeness is both a shield and a hazard. It is easier to hide, but harder to see predators or prey until they are very near. For large creatures, it is more difficult to navigate at speed. Wet ground slips underfoot. Paths are constantly being erased by floods and slides. Behavior, in such a world, must adapt. Nocturnal activity patterns may shift when nights are especially dark and storms frequent. Reproductive cycles may sync more tightly with the seasons of relative dryness, timing nesting and rearing of young to avoid the worst floods. Migratory movements may develop, with some species tracking the shifting belts of rainfall and temperature. These patterns leave faint traces in the fossil record, in the spacing of growth rings in bones and teeth, in the layering of sediments, in the distribution of fossils across latitudes. Interpreting them is like listening for a rhythm in a song that has been mostly erased. The more you listen, the more clearly the rhythm emerges. As the Carnian pluvial episode gives way to the later stages of the Triassic, that rhythm slows but does not stop. The planet has learned a new way to circulate water and carbon, and it will not forget. The Great Rain does end eventually, but its legacy, rivers, lakes, forests, reefs, lineages, continues. Somewhere on a Triassic floodplain, long after the heavier storms are over, a young sauropodomorph dinosaur, one of the early long-necked forms, stretches its neck toward the canopy of a conifer forest. The tree has grown on soil formed from sediments laid down during the Carnian deluges, its roots tapping into groundwater made reliable by the reconfigured hydrological cycle. The dinosaur's bones are built from calcium and phosphorus cycled through those same systems, its muscles powered by sugars produced by photosynthesis in needles that transpire water into the air. Without the Great Rain, this scene might not exist. Yet the dinosaur is not aware of any of this. It simply pulls needles into its mouth, grinds them against worn teeth, and swallows, as clouds drift overhead and distant storms mutter along the horizon. Far downstream, in a warm, shallow sea, waves lap gently at the edge of a reef that has its own origins in the Carnian chaos. Its builders, colonies of scleractinian corals hosting symbiotic dinoflagellates, are now well established, adding layer after layer of limestone to their skeletons. Fish flit among the branches, grazing on algae or snapping up invertebrates. A marine reptile glides past, trailing a shadow over schools of smaller creatures. The reef is no longer a novelty. It is a fixture, a stable structure born from unstable times. The story of the Carnian pluvial episode continues upward in the rock column, into the Nourian and Rhaetian stages of the Triassic, where new volcanic episodes and shifting sea levels will stage further tests. The dinosaurs will continue their rise, other groups will wax and wane, the planet will keep experimenting. For now, though, the echoes of those 2 million years of rain are embedded in every forest, every river, every reef. The world has been broken and reassembled, and the pieces fit together differently than before. If you zoom in again on that transformed world, on a single valley carved into the bones of Pangaea, you can watch what happens in the generations after the worst of the rain begins to ease. The storms are still there, but they no longer feel endless. There are seasons now, blurred and irregular by our standards, but real. Months of near constant showers blend into stretches of heavy clouds without rain, and then into weeks of hot, breezy weather when the ground finally begins to dry. Rivers still swell and shrink, but they are no longer the wild, unanchored torrents that tore up entire landscapes in a single year. Their channels deepen, their banks stabilize, their sediments begin to stack into more orderly layers. In this valley, a broad floodplain stretches out between low hills. Patches of forest anchor themselves on slightly higher ground, where roots can stay above the water table. Between these stands of conifers and tree ferns, open meadows form, studded with cycads and low shrubs. The soil is rich, dark, and deep. Something that would have been almost unthinkable in the hard-baked deserts that came before the Great Rain. A herd of medium-sized herbivorous dinosaurs moves through the clearing. They walk on 2 legs most of the time, balancing their bodies with long muscular tails. Their arms are small but capable, good for pulling branches closer. Their heads are narrow and beaked, tipped with rows of leaves stripped earlier in the day. They are not giants, not yet, but compared to the little dog-sized pioneers that first left prints in the Dolomites mud, they are impressive. 2 or 3 meters from nose to tail, their hips as high as a person's chest. They are in many ways the children of the rain. Their skeletons and muscles are shaped for covering distance, for moving between feeding areas that may be flooded one month and dry the next. Their lungs and air sacs, more efficient than those of their reptilian ancestors, allow them to stay active in warm, humid air that once would have exhausted less capable animals. Their eggs and nesting behaviours, though still simple compared to later dinosaur strategies, are already adapted to soils that can swing between waterlogged and friable from one year to the next. If you follow their tracks across the floodplain, you eventually come to a place where the river has recently shifted course. An older channel, now abandoned, curves in a crescent of stagnant water. Fallen logs and branches line its edges. The mud here is fine and smooth, shaped into tiny ripples by the last slow current that passed through before the river moved on. A new storm has just passed, and the surface of the pool still trembles with rings from raindrops. At the margin, a different set of footprints presses into the soft mud. They are smaller, each one a 3-toed impression only a few centimeters long. A little carnivorous dinosaur has been hunting here, following the scent of frogs or small reptiles that seek refuge in the water. Behind those prints, barely visible unless you lean close, are lighter marks, the impressions of elongated fingers that sometimes touched the ground and sometimes didn't. A juvenile pterosaur has landed, hopped awkwardly, then launched itself again. Its feet left clear marks, its hands barely brushed the surface. In a single patch of mud no wider than a room, the movements of 3 very different lineages are recorded: the browsing herbivores, the stalking predator, the experimental flyer. All of them owe their existence to the ecological upheaval of the Carnian pluvial episode. When sediment covers these tracks and turns to stone, they will become another page in the story that future scientists will learn to read. Far away, on another edge of the supercontinent, something else is happening that will also leave its mark. Pangaea itself is beginning to crack. The great heat stored in Earth's mantle, partially vented through the Rangelia eruptions and their kin, still needs outlets. Beneath the crust, convection currents move sluggishly but persistently, carrying hot material upward and pushing plates apart along lines of weakness. Along what will one day become the Atlantic margin, the first rift basins begin to form, long narrow troughs where the crust is stretching and sinking. These rift valleys are like open wounds on the surface of the planet. Into them water flows, lakes form, some as large as small seas. The climate over these basins is controlled by a mix of regional weather and the particular geometry of the valley. Steep walls, long fetches where wind can drive waves, restricted connections to the broader ocean. Sediments delivered by rivers collect in thick piles, coarse near the edges, finer toward the centre. During the later Triassic, these rift lakes will become some of the best recorders of climate on Earth. Layer upon layer of mud and silt will stack in their depths, each one representing a year, or a decade, or a particular event. In some places the layers will be so regular that they can be counted like tree rings. Tiny changes in their thickness and composition will speak of subtle shifts in rainfall, temperature, and vegetation on the surrounding land. For now, in the aftermath of the Great Rain, they are simply new habitats. On the shore of one of these early rift lakes, a cluster of trees leans out over still water. Their roots are half submerged. Their lower trunks are crusted with algae. In their branches, insects buzz and crawl, some slipping and falling into the water to become food for fish. On a sun-warmed rock, an early turtle rests, its rib cage expanded into a simple shell that offers protection from curious predators. Out in deeper water, large amphibians patrol, their broad heads and tooth-studded jaws reminiscent of ancient lineages that survived earlier extinctions. They lurk near the surface, gulping air and waiting for prey. Sometimes they're joined by semi-aquatic reptiles that paddle with limbs rather than fins, equally at home sliding through flooded forests or basking on sandbars. These lakes are fed not only by rainfall and rivers, but by groundwater, emerging from fractures in the rift walls. The chemistry of that water can be unusual, rich in dissolved minerals and gases. In some pockets, microbial mats flourish, feeding on the chemical energy. In others, conditions become hostile, stagnant bottoms where oxygen is scarce, where the remains of plants and animals accumulate in thick black ooze. When these oozes are buried by later sediments and heated, they will become source rocks for hydrocarbons. Tens of millions of years later, humans will drill into them and draw up oil that was formed from the bodies of organisms that lived in the wake of the Carnian rains. But here, within the Triassic night, all of that is still unimagined. Back on the open plains of central Pangaea, the sky begins to clear more often. Sunsets stretch unbroken across vast horizons, the air hazy with moisture but not always release. Even without constant rain, the atmosphere still carries the memory of those wet millions of years. Clouds form easily, convection stirs, afternoon showers remain common, dawn mists hug the lowlands. The plants that have come to dominate this world are masters of these conditions. Conifers in particular have diversified. Some species grow tall and straight, forming emergent crowns that intercept the first light of morning. Others spread broader crowns, casting deep shade below. Their needles are thick and resinous, resistant to herbivory. Many contain chemical defenses that make them unpalatable or even toxic to some animals. When branches break or insects chew, resin oozes out, trapping invaders and sealing wounds. Over decades and centuries, that resin can accumulate in pockets and cracks, slowly hardening into amber. Inside one such drop of resin, a small winged insect struggles. It has been feeding on spores and pollen, flying from cone to cone in search of food. A break in the bark near a resin duct has dribbled sticky fluid onto the surface. The insect lands, becomes entangled and cannot pull free. Its wings are pinned, its legs flail. More resin flows over it, and soon it is sealed in a little golden coffin. Layers of resin build over it, entombing its delicate structures in extraordinary detail. When this piece of amber is later buried and fossilized, the insect inside will be preserved so clearly that future scientists will be able to see the hairs on its legs and the facets of its compound eyes. It is a snapshot of an ecosystem that has been stable long enough to produce intricate mutualisms between plants and insects, and dynamic enough to keep those partnerships evolving. Pollination syndromes in a primitive form are already beginning to emerge. Not all plants in these forests rely on wind to spread pollen. Some produce sticky spores and grains that cling to insect bodies. Certain insect lineages develop specialized mouthparts and behaviors that make them better suited to visiting particular plant structures. The rewards are modest. Tiny drops of nutrient-rich fluids, patches of spores to eat, but the selective pressure is constant. Efficient pollinators leave more offspring. Plants that attract them reliably leave more seeds. The Great Rain did not invent these relationships, but by expanding forests and increasing environmental complexity, it gave them room to evolve more rapidly. In the oceans, the partnership between corals and dinoflagellates continues to build on its initial success. Early reef systems survive local disturbances, storms, sediment influxes, episodic warming, and recover. Their three-dimensional frameworks provide refuges from which life can rebound after local setbacks. In time, more and more lineages come to depend on the stability of these structures. Certain fish species evolve body shapes and behaviors suited to darting among coral branches. Some develop strong jaws and specialized teeth for scraping algae off hard surfaces. Others become nocturnal, feeding in open water at night and retreating into the reef's crevices during the day. Crustaceans take on the role of cleaners, picking parasites off larger animals in exchange for safe access and food. Starfish and sea urchins occupy their own niches, some grazing on plant life, others scavenging or preying on slow-moving invertebrates. Each of these roles is shaped by the physical presence of reefs that were born during the chaos of the Carnian. When conditions in the broader ocean shift, when upwelling patterns change, or when temporary anoxia develops in deeper waters, these reef communities provide relative stability. It is not that they are immune to disturbances, but that their complexity allows for more routes to recovery. If one species declines, another may partially fill its role. The system flexes rather than snapping. The same principle plays out on land. On one side of a broad river, a pure stand of conifers covers a hillside. On the other, a more mixed woodland spreads. Conifers, tree ferns, cycads, and some early seed plants with broad leaves. When a lightning strike ignites a fire during a rare dry spell, the pure stand burns intensely. Resin and needles serve as fuel. Many trees are killed to the roots. The soil, once shaded and damp, is exposed and baked. Across the river the flames behave differently. In dense, damp patches of tree ferns, progress is slow. In open cycads groves, heat builds, but the plants are adapted to occasional scorching and can re-sprout from protected buds. Some conifers die, others survive in small groups that act as seed sources. The mosaic of plant types creates a mosaic of fire intensities, After the burn, recovery is faster in the mixed forest. Multiple lineages are ready to colonize bare patches. Varied root systems stabilize the soil. Different leaf litter types support diverse microbial communities that rebuild fertility. Animals have more options for shelter and food. Within a few seasons, the hillside is green again, though its exact composition has shifted slightly. The conifer monoculture, by contrast, regenerates slowly. Seeds must travel farther, soils erode more before plant cover returns. If another disturbance arrives too soon, an especially heavy rain, a second fire, the stand may struggle to re-establish, leaving the door open for a different plant community to move in. Again and again, complexity proves to be a form of resilience. The Carnian pluvial episode took a world that was simpler, harsher, and more uniformly constrained, and forced it through a crucible that rewarded diversity of form and strategy. The result, as the episode fades, is a biosphere with more moving parts, more backup systems, more ways of absorbing shocks. That doesn't mean the planet is safe from future crises. Far from it. Already subtle hints of the next great challenge are appearing on the horizon of deep time. The tectonic forces that began to split Pangaea during the Carnian and Nourian stages are not finished. In the distant future of the Triassic, a massive outpouring of lava will flood vast regions of what is now eastern North America, northwestern Africa, and parts of Europe and South America. This event, which we now call the Central Atlantic Magmatic Province, will trigger yet another round of greenhouse warming, ocean acidification, and extinction. But that is still tens of millions of years away. Between now and then, the descendants of the lineages shaped by the Great Rain will continue to explore evolutionary space. The early sauropodomorphs will gradually lengthen their necks and tails, enlarge their bodies, and refine their limb bones into columns capable of supporting unimaginable weight. Theropods will diversify into nimble hunters, some small and fast, others massive and powerfully built. Ornithischians will begin experimenting with new ways of grinding plant material, with novel jaw joints and dental batteries. Early mammals will refine their hearing and chewing apparatus, develop more complex dental patterns, and adopt nocturnal lifestyles that allow them to coexist alongside dinosaur giants. Pterosaurs will gain confidence in the air, increasing in size and range. Crocodilians will try on multiple lifestyles, terrestrial, semi-aquatic, fully aquatic, before settling into the forms we recognize more readily. Each of these experiments builds on the ecological scaffolding erected during the Carnian rains, the forests that now lace together the continents, the soils rich with organic matter, the reefs that lace the shallow seas. These are the stages on which later dramas will play out. In the quiet spaces between storms, the planet continues to write its story into stone. A log falls into a river, becomes waterlogged and sinks. Over time, minerals seep into its tissues, replacing organic molecules with silica and other compounds. The log turns to stone, preserving the textures of bark and growth rings. When future paleontologists cut and polish it, they will see that during the years of the Great Rain, the rings are faint and tightly spaced, evidence of stressful conditions, rapid changes in water availability, and crowded forests. In the years after, the rings widen and stabilize, marking a different balance. Elsewhere, a layer of volcanic ash settles over a region during one of the later eruptions that punctuate the tail end of the Carnian pluvial episode. Its chemistry is distinct, containing a particular mix of trace elements. As sediments continue to build above it, that ash layer becomes a reference horizon. By matching it across distant locations, scientists millions of years later will be able to correlate events on different continents, stitching together a global story. Tiny shells of marine plankton, each smaller than a grain of sand, fall continuously through the water column in the open ocean. They settle into thick blankets on the seafloor. Their chemistry records the temperature and composition of the seawater in which they grew. Their abundance waxes and wanes with productivity. These quiet snowfalls of microscopic bodies are the metronomes of deep time, ticking away the rhythms of climate and life. Everything is being recorded, even if no one is there to read it yet. The most humbling part is that from the perspective of the planet, the 2 million years of the Carnian pluvial episode are not an aberration, not a glitch. They are one variation among many in Earth's long pattern of feedbacks between geology, atmosphere, ocean, and life. Supercontinents assemble and break apart. Large igneous provinces erupt and cool. Ice ages advance and retreat. Through it all, life responds, sometimes with crises and collapses, sometimes with bursts of creativity and expansion. The Great Rain is one of those bursts. If you could hold the entire 4.5 billion year history of Earth in your hands like a book and riffle through the pages, the Carnian pluvial episode would flash past as a thickened section where the colour and texture suddenly change. Before it, the chapter of early Mesozoic recovery is written in subdued tones. After it, the page explodes with new hues, deep greens of conifer forests, bright turquoise of shallow reef seas, warm reds and browns of dinosaur-dominated floodplains. And if you focus in even further, if you let your imagination walk those floodplains and swim those seas, you can feel the lingering presence of the rain everywhere, in the shape of river channels that wander more widely than before, in the chemical composition of soils, in the physiology of animals whose ancestors learned to cope with extremes of humidity and heat. You can feel it in the way forests hold onto water, in the way reefs soften wave energy, in the way the atmosphere now contains more oxygen and less carbon dioxide than it did before. The Great Rain did not just drench the planet, it retuned its systems. Even now, in the far future where you sit listening and drifting, the echoes remain. The limestone in the Alps that first puzzled Wolfgang Schlager and Matthias Schollenberger, the coal seams in distant continents, the kaulinite clays that formed under relentless tropical downpours, these are all remnants of that time. The very idea that climates can shift quickly, that ecosystems can flip from one state to another and stay there for millions of years, comes in part from studying episodes like the Carnian. As your mind moves through this story following rivers and storms and lineages, it begins to take on a similar rhythm. Long, slow build-ups of change, punctuated by moments of sudden transition. Gradual adaptations, interrupted by opportunities seized and paths abandoned. The Great Rain becomes less a remote event and more a pattern, a way the universe has, from time to time, of forcing possibility into reality. The dinosaurs grazing in the renewed forests do not know any of this. They lower their heads, tear at ferns and cycads, and swallow. The pterosaurs skimming above lakes are concerned only with the next fish flickering beneath the surface. The corals building reefs in warm, shallow seas respond to light and chemistry, unaware that their cities will one day become mountain ranges. Yet every step they take, every mouthful they eat, every calcite skeleton they lay down is part of a chain of consequences that stretches from those 2 million years of rain into futures they cannot imagine. The story continues quietly, through each heartbeat and each drop of water that falls from the sky. In the millions of years that followed the Great Rain, the planet settled into its new rhythm. The worst of the volcanic fury eased. The atmosphere, once overloaded with greenhouse gases and ash, began to clear. Sunlight fell more evenly across the continents. Storms still rolled in from the seas, but now they came in patterns, in seasons, not in the ceaseless chaos that had once drowned a supercontinent. If you could have watched the Triassic world on fast-forward from orbit, you would see something subtle but profound. The colours of the land would change. The harsh reds and browns of the old desert Pangaea would fade, replaced by muted greens spreading like ink through paper. Forest belts would thicken along river systems. Coastal plains would darken as conifers, cycads, and tree ferns dug their roots into new soil. Broad swathes of interior land, once empty and wind-scoured, would gradually shift from pale to deep green, broken by ribbons of silver where river networks gleamed. Zoom in again, and you would see that those rivers were no longer strangers in the landscape. They had carved permanent homes for themselves, meanders looping through floodplains, deltas feathering outward where they met the sea. Where the soil was deep and the ground gently sloped, wetlands formed. Reed-choked marshes, peat-forming bogs, quiet oxbow lakes cradling still water under overhanging branches. Life didn't simply live beside these rivers anymore. It organized itself around them. Herds of herbivorous dinosaurs used the floodplains as highways, following familiar paths from feeding grounds to water sources. Predators shadowed their movements, leaving their own tracks alongside. In the trees, early mammal ancestors hunted insects and hid from sharp-toothed snouts below. Dragonflies patrolled the air. Frogs called from the shallows. Turtles basked on half-submerged logs. Everything pulsed to the slow beat of the new climate system, the rise and fall of river levels, the approach of seasonal storms, the long dry spells that followed. And deep beneath all this, in the layers of rock forming grain by grain under ancient seas, the memory of the great rain was locked in place. The dark, clay-rich horizons that first confused geologists in Austria did not stop forming overnight. For a long time they alternated with lighter layers, each cycle representing another swing between wet and dry, another phase of erosion and stability. If you were to slice down through these layers with an impossibly sharp blade, you would see history written as a barcode. Dark, light, dark, light. Each stripe a pulse of climate. Over millions of years the pulses grew less extreme. Volcanism slowed. The atmosphere's greenhouse burden gradually declined as forests and swamps kept locking carbon away. The kaolinite-rich clays that spoke so clearly of relentless tropical weathering grew thinner, then rarer, then disappeared. The Carnian pluvial episode, after reshaping the planet for nearly 2 million years, finally loosened its grip. But the world did not go back to what it had been. It couldn't. Too much had changed. You cannot erase forests that have spread across continents, or reefs that have turned shallow seas into limestone factories, or lineages that have diversified under new rules. By the time the last of the Carnian rains faded, the Earth had crossed a threshold. The carbon cycle worked differently now. Plant roots penetrated deeper into rock, accelerating chemical weathering and drawing more carbon dioxide out of the sky. Soils stored organic matter that would once have washed straight into the sea. Coal swamps, though not as widespread as in the ancient Carboniferous, hummed quietly through lowlands, turning dead vegetation into long-term carbon vaults. The oceans breathe differently too. New plankton groups, the coccolithophores and dinoflagellates that had appeared during the Great Rain, had settled into their roles at the base of food webs. Every time they bloomed and died, their tiny shells and bodies helped shuttle carbon to the deep sea. Reefs locked away vast amounts of calcium carbonate, rearranging the chemistry of coastal waters. These changes nudged Earth toward a more buffered, more self-regulating state. Not perfectly stable, nothing in deep time ever is, but more resistant to sudden swings than the desert planet that came before. Out of this new stability, the rulers of the Mesozoic age emerged, those small, quick dinosaurs whose tracks first spiked in the Dolomites mudstone had descendants that grew taller than houses and longer than city buses. Within a few tens of millions of years, sauropods were roaming floodplains as living architecture, necks like cranes, legs like columns, bodies so massive that each step reshaped the paths of rivers and the distribution of plants. Other dinosaur lineages branched out alongside them. Some evolved thick armor plates, turning their bodies into walking fortresses. Some developed beaks and intricate dental batteries, grinding plant matter with the efficiency of modern grazing mammals. Predatory forms honed their senses and jaws, learning to hunt creatures larger than anything that had walked before. Bird-like theropods refined feathers that had begun as simple filaments into complex structures, useful for insulation, display, and eventually gliding and powered flight. On the edges of rivers, in the canopies of the conifer forests, under the eternal summer light of Mesozoic low latitudes, life took full advantage of the world the Great Rain had opened. If you examine the bones of these creatures, the hollow vertebrae of sauropods, the air-sac-riddled skeletons of theropods, the thin-walled skulls of early birds, you'll find clues to another inheritance from the Carnian. High humidity and a warm, oxygen-rich atmosphere had favoured respiratory systems that could exchange gases rapidly and continuously. Air sacs, unidirectional lung airflow, high metabolic rates. All those features made dinosaurs and their kin remarkably effective at moving, feeding, and growing in the climates that followed the Great Rain. The very biology that let them dominate the Jurassic and Cretaceous was, in part, a refinement of strategies that let their ancestors survive in the suffocating humidity of a world under constant storm. As the dinosaurs took centre stage, many of the earlier Triassic lineages either dwindled or adapted to more specialized roles. The mammal ancestors, for example, shrank into nocturnal niches, trading bigness for sensitivity. Under starlit conifer branches they sniffed, listened, and crept. Their bones recorded a shift toward warm-bloodedness, parental care, and complex brains. In the shadow of dinosaur giants, they sowed the seeds of future possibility, but for now they remained side characters, surviving in spaces the dominant reptiles ignored. Time flowed on. The Triassic gave way to the Jurassic, not with a single dramatic curtain fall, but with a slow tightening of tectonic stresses. Pangaea's cracks widened, rift valleys deepened. Eventually, along what would one day be the Atlantic margins, lava began to pour out in astonishing volumes. The Central Atlantic Magmatic Province, another of those vast flood basalt events, sent fountains of molten rock surging up through fissures. Sheets of lava spread for hundreds of kilometers. Gases belched into the air once again. Carbon dioxide, sulfur dioxide, halogens. For a moment it must have seemed like the ghost of the Carnian was returning. Climate lurched. The oceans warmed and acidified. An extinction unfolded, this time at the Triassic-Jurassic boundary, removing many competing reptile groups and clearing still more ecological space for dinosaurs. But even this crisis did not undo the work of the Great Rain. The forests, soils, and reefs that the Carnian pluvial episode had midwifed gave the biosphere a deeper reservoir of resilience. The extinction was serious, but it did not erase complexity. Instead, it resorted it, shifting the balance once more toward lineages already proven adaptable. From there, Earth slid fully into the age of dinosaurs that most of us picture when we hear the word Mesozoic. Stegosaurs on fern-filled plains, long-necked giants browsing from high conifer crowns, swift-footed predators darting through river valleys, early birds flapping awkwardly over lagoons. Rain still fell, of course. Storms still lashed coastlines and flooded lowlands. Climate still shifted over millions of years. But never again would the planet experience quite the same sustained, global transformation as during those 2 million Carnian years. The Great Rain became a completed chapter, its consequences still unfolding, its exact shape sealed in stone. Fast forward far into the future, past the peak of dinosaur diversity, past the late Cretaceous seas that flooded continents and shimmered with ammonites and mosasaurs, past the day when a mountain-sized rock fell from space and ended the dinosaurs' reign in an instant. In the quiet that followed, as birds and mammals inherited the world, the environmental foundations laid in the late Triassic still mattered. The distribution of continents inherited from Pangaea's breakup still structured climate. The carbon cycle, tuned by forested landscapes and life-rich oceans, still buffered extremes. Mammals, freed from dinosaur competition, expanded into forms and lifestyles their shrew-like ancestors could never have imagined. Some returned to the sea, others took to the air. Many grew to sizes that would have seemed impossible during the Carnians' early experiments. Primates emerged in forest canopies, their hands and eyes adapted to three-dimensional worlds of branches and leaves. Eventually, deep in one of those primate lineages, a brain evolved that could think about time in more than one direction. A brain that could imagine the past, analyze the present, and worry about the future. A brain that would one day send individuals into mountain ranges with notebooks and rock hammers, searching for traces of stories long finished. When those geologists in the Alps chipped at the limestone and found the dark, clay-rich layer that did not fit, they were, without knowing it, closing a loop that had begun hundreds of millions of years earlier. The storms that had drenched Pangaea, the rivers that had carved new paths, the forests that had spread into desert, had all conspired to leave a mark subtle enough to hide for eons, yet persistent enough to be uncovered by one particularly curious species. And then, when the evidence had been gathered from Austria and England, from Israel and Utah, from Italy and China and South America, that same species did something stranger still. It told itself a story about the rain. Piece by piece, data point by data point, humans reconstructed the Carnian pluvial episode, the timing of eruptions, the chemistry of ancient oceans, the types of plants and animals that rose and fell with the changing climate. They gave it a name. They plotted it on charts. They argued over its exact duration and intensity. They turned it into lectures and textbooks and eventually into documentaries and sleep stories, the one you're listening to now. In doing so, they added one more consequence to the long chain triggered by the Rangelia eruptions. Those eruptions had not only helped create forests, reefs, and dinosaurs, they had, through countless indirect steps, ultimately helped create minds that could imagine forests, reefs, and dinosaurs. Minds that could compare their own, very recent climate anxieties to the deep history of Earth's past. Because once you know that it rained, almost without stopping, for 2 million years, once you understand that this planetary upheaval reset ecosystems, rewired cycles, and reshaped the entire trajectory of life, your own moment in time feels different. On human scales, weather can seem random, overwhelming, one bad storm, one flood, one drought. On deep time scales, weather becomes climate, and climate becomes narrative. The Carnian pluvial episode is one chapter in that narrative. The ice ages that sculpted the world much later are another. The gradual warming and cooling rhythms of the Cenozoic, the rise and fall of sea levels, the spread and retreat of forests and grasslands. They're all verses in the same long poem. Right now, you live in a stanza that is changing unusually fast. In just a few centuries, a flicker of geological time, human activity has begun to add greenhouse gases to the atmosphere at a rate that rivals some of the more abrupt events in Earth's past. The water cycle is responding, storm tracks are shifting, heat waves and deluges are both becoming more extreme in many regions. It is natural in such a moment to feel small and anxious, to lie awake at night wondering what kind of world is coming and how much of it is already decided. This is where stories from deep time can offer an unexpected kind of comfort. They do not tell you that change is harmless. The Carnian pluvial episode was not gentle. It killed species and erased entire ways of life. They do not tell you that everything always works out. Many evolutionary experiments never recur once they are gone. What they do show you is that Earth is not fragile in the way an ornament is fragile, prone to shattering at a single blow. It is resilient and restless, constantly reorganizing. Life, once it exists, is astonishingly good at filling space, exploiting opportunity, and building complexity on top of disruption. And you, as a human being with a mind capable of imagining this grand story, are a product of that resilience. Every cell in your body belongs to lineages that threaded their way through the Carnian storms, past later extinctions, through ice ages and heat spikes, through all the accidents of history that could have gone differently. When you listen to the rain on your window tonight, you're hearing a very tame, very gentle echo of forces that once reshaped continents. The drops sliding down the glass are doing on a tiny scale what the Carnian rains did on a massive one. Eroding surfaces, carrying minerals, feeding rivers, supporting life. The clouds outside your home are part of the same atmospheric machine that once thickened into permanent overcast over Pangaea. The water molecules in those clouds have almost certainly been through countless cycles of evaporation and precipitation since the Triassic, through oceans, glaciers, lakes, and living bodies. Some of them may even have fallen during the Great Rain itself, then been buried in ice or trapped in minerals only to be released again millions of years later. In that sense, the boundary between then and now is not as firm as it feels. The world of the Carnian and your world share materials, patterns, and even echoes of emotion. Awe at storms, fear of floods, gratitude for water when it arrives on time and in the right amount. You're connected to that story simply by being alive on this planet. As you lie here, letting the details settle in your mind, the Austrian geologists with their puzzling dark layer, the supercontinent baked by sun, the volcanic fires under the Pacific, the forests marching across former deserts, the tiny dinosaur tracks in Italian mud, the first reefs glowing under Triassic seas. You're doing something very old and very human. You are turning facts into meaning. You are placing yourself, quietly and without effort, into a narrative that is far bigger than any single life. And in that placement there is room to rest, because for the hours that you sleep, the story will go on without you needing to hold it. Clouds will still form whether or not you are awake to watch them. Rivers will still run, silently rearranging grains of sand as they always have. Continents will continue their slow migrations, imperceptible on human scales, but over millions of years, as inevitable as a heartbeat. The dinosaurs that rose in the wake of the Great Rain are long gone, but the consequences of their era remain in birdsong, in soils enriched by ancient life, in rock layers that shape the routes of modern highways and railways. In the same way, your own actions and thoughts will ripple outward in ways you will never fully see. But tonight, you don't have to track them. You've walked far enough for one evening. You've followed a storm through 2 million years of time. You've watched deserts drown and forests grow. You've seen small, overlooked creatures become rulers of the world, and you've traced how those events eventually led to you, here, listening in the dark. Now, as your breathing slows and the edges of your awareness soften, you can let the images fade. The red glow of volcanic horizons, the endless curtains of rain draping Pangaea, the first conifer forests rising out of mud, the little three-toed tracks pressed into lagoon floors, the reefs blooming in warm, nutrient-rich seas. All of it can recede into the background hum of deep time. Above you in the real world, the sky may be clear or cloudy. There may be rain on your roof or nothing but stillness. Either way, the atmosphere is calm compared to what it has known. The planet is quiet, at least for tonight. You're safe inside your small shelter on the surface of this old, restless world. You can imagine the rain if it helps, the gentle patter, not the roaring deluge. You can picture a thin silver thread connecting each drop back through uncounted cycles, back through oceans and rivers and storms, all the way to that ancient episode when the sky opened and refused to close, and as you do, you can allow yourself to drift. Out of the Triassic forests, away from the reefs and river plains, back through the long corridors of time, until you return fully to your own life, your own bed, your own breath. The story of the 2 million year rain will still be there in the rocks, waiting. The planet will keep turning, the water cycle will keep moving, life will keep unfolding its possibilities. For now, your only task is simple. Let your eyes grow heavy. Let your thoughts slow. Let the ancient storms recede into a gentle, distant murmur. And held by a world that has weathered so much and still remains astonishingly alive, allow yourself to rest.